This video is part 2 of valence shell electron pair repulsion theory. So we are starting with Trigonal Bipyramid, which is 5 electron groups. And the thing about Trigonal Bipyramid is this involves central atoms that do not obey the octet rule. They have more than an octet. Therefore, this shape will only be around when you have an element in the center that is row 3 or higher. Okay, and that's because it requires higher than an octet around the central atom, so it is row or period 3 elements and higher. Okay, and phosphorus is in row 3, so phosphorus is commonly in this shape, so is sulfur and some other elements in row 3 and greater. Alright, so remember there were 2 different angles in Trigonal Bipyramid, and one of them was 90 degrees, so I'm counting the 2 wedged chlorines and the one going to the right as being in a plane that is horizontal, and this chlorine goes up and this chlorine goes down. Okay, so the angle here is 90 degrees, and this is the only one with the only shape with 2 different angles. And then the angle between 2 in the plane is 120 degrees, because those in the plane are much like trigonal planar. Alright, so there's 2 different angles in this geometry. Alright, so there's 3 groups in a plane at 120 degrees nominally, and the last 2 are at 90 degrees to that plane. Alright, so let's look at the options for molecular shapes. And we're going to talk about, obviously one of the shapes is just Trigonal Bipyramid, which is what this one is. So this one shown already is the Trigonal Bipyramid shape. So many times the electron groups and the shape will be exactly the same thing. And that will happen whenever all the electron groups are bonds to some atom. Okay, these are all bonds. There's no lone pairs. So the shape is Trigonal Bipyramid, and so is the electron group geometry. Alright, but let's go down and talk about those where it's not the same. It's not Trigonal Bipyramid shape, it's Trigonal Bipyramid electron groups. Okay, so first we'll do one where just one of the groups is a pair of electrons. Okay, and SF4 is an example. Okay, so it has these 3 in the plane. One of them is an electron group. I can draw it like a big electron cloud. And then it has a fluorine up and down. And this is known as seesaw. Okay, so the reason it's a seesaw is if you flipped it on its side and made these 2 fluorines kind of like be legs on a table, you could actually have a teeter-totter or seesaw between these 2. And that's a lot easier to see when you work with models, but it makes a seesaw shape. Alright, if you have 2 pairs of electrons in a 5 electron group shape, electron geometry, you will have the 2 electron groups will, just like before, the electrons that are lone pairs will repel more than the bonds. So they will tend to take the positions where they can be further apart. Remember, the ones that go up and down are 90 degrees from the plane. These are 120 from each other, so the lone pairs will always go in the planar positions, not the up and down. Okay, therefore, what's left is a T-shaped molecule, and we simply call it T-shaped for its shape. And when you have 3 pairs of electrons, all 3 will go in the planar part, and you'll have a bond going up and a bond going down, and that actually is just linear. The shape is linear. Even though there's electron groups there, the shape is linear. Okay, so let me make it clear. These are molecular shapes. and they are under the category of the trigonal bipyramid electron groups. And for these two particular cases, T-shaped and linear, the lone pairs, you must have the lone pairs in the planar positions. Otherwise you will come up with the wrong shape. Alright, we have one more electron group geometry, and that is octahedral. And remember, that is for 6 electron groups around a central atom. This also requires more than an octet. In order to have 6 groups, you got to have more than an octet because each group has 2 electrons. And so this also occurs for row or period 3 and higher. So sulfur is in period 3, so it will do this. We can draw it so that we have 6 fluorines. This is sulfur hexafluoride. 1 goes up, 1 goes down, and 4 in a plane where these 2 come out at you, and these 2 are going back into the page. We can also draw it a number of other ways, one of which is something like this, where we put the sulfur in the middle, we put a fluorine up and a fluorine down, and I'm going to run out of time here. I'm going to do this again and try to do it faster. Okay, so we have a sulfur, we have a something like this, we have an F up, an F down, and we have 4 in the corners of this square. Okay, so that's one way of drawing it. It makes it more clear, and all angles are 90 degrees, at least all between adjacent fluorines. Okay, so that shape, sulfur hexafluoride, is octahedral. Again, when all the electrons groups are bonds to an atom, your shape will be the same as your electron groups. Okay, but some of those electron groups can be lone pairs. If one of them is a lone pair, you have something like IF5, and so you have 1 lone pair and 5 fluorines, and this is known as, these 4 are in a square, and you have 1 going below, and if you think of flipping it upside down, you would actually have what we call a square pyramid, like that, about like that. Okay, so that's called, guess what? Square pyramid. And if you have, and the nominal bond angles are still 90 degrees, but the actual bond angles will be less because a lone pair squishes the others a little bit more, squishes them together. Okay, if you have 2 lone pairs, remember the lone pairs want to get as far apart as possible. So one will go somewhere and the other one will go on the opposite side. So everything left, the bonds, will be in a planar square. Guess what we're going to call this one? Square planar. Okay, so these are the molecular shapes. Whoops, not good. And those are shapes that are under the general electron group category of octahedral. Alright, let's try some stuff. Use VSEPR theory to predict these shapes. So I already did the Lewis dot structures for you and predict their shapes. Alright, so let's count how many groups are on the central atom. 1, 2, 3, 4, 5. So it's 5 E groups, which means the electron group geometry will be trigonal bipyramid. So I'm going to write that as E groups. That is not the shape. Trigonal bipyramid electron groups. And the electrons will take the planar parts of the group. Remember, there's 2 different angles in trigonal bipyramid. So the electrons will all take the planar part, because they want to get as far apart as possible, so we can draw it something like this for the planar parts, and then we can draw a chlorine up and a chlorine down. And since this is a negative, we still need to draw, I don't think I had a good dot there. Okay, I still need to draw the minus sign outside of brackets, just like in a Lewis structure. So the 3 lone pairs are in planar positions. The 2 chlorines are opposite each other, and the molecular shape is linear, and the bond angles would be 180 degrees, and they would not vary from that. There's nothing to make them vary because the 3 lone pairs are in equal positions. All right, let's go to our other example. This has 5 electron groups around the chlorine as well. So it's also trigonal bipyramid in the electron groups. But what is the shape? We have 2 pairs of electrons. Here we had 3. Now we have 2 pairs of electrons. Those 2 pairs of electrons will take those equatorial positions, take the planar positions, so that would be something like this. Oops, should be Cl. And therefore the shape is nominally T-shaped. But the bond angles will actually not be exactly 90 degrees. The lone pairs will push them a little bit, so the actual bond angles will be slightly less than 90 degrees. We don't know the exact value. I don't know the exact value. But it's something like, you can predict that it's less than 90. All right, so let's summarize the shapes. All right, so we have on the left column, we have a number of electron groups. The central, or the next column over, I have listed the electron group geometry, so linear, trigonal planar, tetrahedral, trigonal bipyramid, and octahedral at the bottom. Okay, now with with molecular shapes, we can talk about when there's no lone pairs, 1, 2, and occasionally sometimes 3. All right, so if there are no lone pairs, then the electron group geometry is exactly the same as the molecular shape. So I can simply copy all these names over. If there's no lone pairs, then the shape is the same as the geometry of the electrons. I'll go down, do octahedral. I'm just going to abbreviate. Okay. If there is 1 lone pair, that doesn't happen with linear. There aren't going to be any lone pairs with linear. Okay, if there's 1 in trigonal planar, then it's bent. And that's as far as we go with that. In tetrahedral, if there's 1 lone pair, that is trigonal pyramid. I should rewrite that. Trigonal pyramid. And if there are 2 lone pairs, then that is bent. And there are not 3 lone pairs. All right, for 5 electron groups, if 1 of them is a lone pair, it's seesaw. If 2 is a lone pair, it's T-shaped. And if there's 3 lone pairs, this one is linear, which is very different than the linear with 2 electron groups. But the molecular shape is the same. All right, for octahedral, 1 lone pair will get you a square pyramid, and 2 lone pairs will get you square planar, and we're not going to talk about 3 lone pairs because that isn't one of the most common shapes. So we're listing the most common. All right, let's talk about molecular polarity, which is based on shapes. So bond polarity is how polar bond is, and we've talked about that in reference to covalent bonds. So we say that like a fluorine-fluorine bond is completely non-polar. There's no uneven distribution of charge. We can talk about a bond that consists of 2 different elements, and since they have different electronegativities, okay, different electronegativities, then they will have an uneven charge distribution. Okay, we talked about that before in terms of delta plus and delta minus. Okay, but we can also say that because there's a difference, the uneven distribution of charge, it's polar. There are poles in the electron density. All right, so that's bond polarity. We can use those ideas and apply them with shapes to figure out molecular polarities. Because sometimes a polar bond, if combined with another polar bond or several polar bonds, will cancel the polarity of the molecule as a whole. Okay, so what we care about now is molecular polarity. And so the question is, do the bond polarities cancel? That's basically the question you're asking. And if they cancel, then it's not polar. All right, so let's look at carbon monoxide, and I'm not showing dots, just showing shapes. Carbon monoxide has a carbon and an oxygen. There's a polarity to that bond. There's nothing to cancel it. So this is a polar molecule. However, you can have a carbon dioxide, and since we know it's linear, we know that the polar bond for, and I'm going to use the other terminology. Okay, up here we can do that too. If there's a polar bond between carbon and oxygen, and there's another polar bond between carbon and oxygen, and they are equal and opposite, so they cancel each other. And overall, the molecule is, let me write it in, non-polar, because they cancel. Okay, so let's look at some more complicated molecules. BF3, the fluorines are all directed in 120-degree angles. And you can kind of think of this in terms of a tug of war. Think of the three fluorines pulling on ropes, pulling that poor boron, and if the pull is such that the boron would sit still, then it's nonpolar. Okay, so these three would actually cancel each other, and the boron would not move at all in a tug of war, so it is nonpolar. A methane molecule has tetrahedral shape, and it's not real obvious in this type of drawing, but since all the angles are actually the same, they all pull equally, and it's nonpolar. SF6, same thing. All these fluorines, like this one pulls the opposite. This one pulls, that one pulls the opposite. This one pulls, that one pulls the opposite. So these, whenever you have molecular shapes such that all electron groups are bonds to the same atom, these are all bonds to fluorine, all bonds to hydrogen, all bonds to fluorine, then you will have nonpolar molecules. Okay, all electron groups are bonds to the same atom. That will make it nonpolar. Look down here at ammonia, NH3, and you'll see it is polar. The hydrogens, if they were pulling on this, nitrogen would go down, right? There's nobody up above to pull it the opposite way. So this one is polar. And that's because there's no bonds at all the electron groups. Here's SF4. It's also polar. Okay, these two would cancel each other, but these two, the net would be pulling that way. Okay, so this one's polar. Now, so in most cases, when you have lone pairs, you'll find it to be polar, but there are exceptions, and one of them is if you have octahedral electron groups, okay, 6 electron groups, we have 4 bonds to fluorine and 2 lone pairs, one of them goes up, one of them goes down, and the fluorines are actually all opposite each other, so this actually is nonpolar. So anytime you have all your groups, all your electron groups bonds to the same thing, it's nonpolar, and there are a few other cases where they will cancel, and this is one of them.